Good evening, everyone. Welcome to the session. So today we are going to start a new session. Today's topic is Process Design Fundamentals and PFD. Our trainer for today is Mr. Rajaram U. He is working as a lead process engineer in Elixir Engineering. Elixir Engineering is a sister company of iFluids Engineering functioning in Oman. Mr. Rajaram, you had 16 years of experience in performing plant operations, pre-commissioning, commissioning, and performance monitoring activities. He has been an integral part of several turnkey projects of Elixir Engineering for the past years. We heartily welcome you to the session, sir. Thank you for joining us today. So before we move on to the session, I would like to request you all to actively participate in the session. Please ask your questions, and if we are sharing a Slido link, you can post your questions in the link if you are not comfortable in asking in public. So there's an option for you. Please make it interactive. It is going to be a great section. Also, please do not comment your names in the chat box for attendance marking. We'll be sharing an attendance form separately. The names that you're sharing in the chat box won't be considered for your attendance. So please make note of that as well. So we'll have a dedicated Q&A session at the end of the training for 30 minutes. So all your doubts will be cleared at that time. Please make sure you ask questions. Rajaram sir, I kindly request you to start the session.
Thank you, ma'am. Thank you, ma'am. Hope my screen is visible to everyone. Okay, ma'am. So, ma'am, when can I start? Whether all the participants join?
So you can start, sir. Can you disable the annotations?
Okay, just.
Yeah.
Yes, ma'am. Done, ma'am.
Okay, so you can proceed with the training, sir. Thank you.
Thank you, ma'am. Okay, ma'am. So I heartily welcome the participants. Hope all the participants are the recently passed out engineers, chemical engineers. I heartily welcome to this training session, Introduction to Process Engineering Design. So I want this session as an interactive session. In between, I will ask some few questions. You can ping your answers through the chat box. Hope you people are listening through your laptop or mobile. So you will be having option to text through the chat box. So shall I start now, students? Okay, I will start now. So this session is for the overall brief of the process engineering design. What the design engineering company does for a project. So the chemical engineers who are working in a design company are called as this one process engineers. So if the chemical engineers are working in a production company, so they a production company where they are involved in operation team, they are working with the operation team, they are called as operation engineers. So if the chemical engineer working in a production plant in a technical service, they are also called as a process engineer. So even the chemical engineers will be called as a commissioning engineer if they work only for the commissioning activities for different projects. So first, the process technology development. The first slide is process technology development. The process involves the conversion of naturally available raw materials into products used in our day-to-day life. Examples such as sugar from sugarcane, LPG, kerosene, petrol, diesel from crude oil, cement from clay and limestone. So generally, a process means a conversion of one material to another material, two set of steps. So in industry, we call it as a process. In the process is, if we see literal meaning for the process, it will be like similar, but industry, we call it as this sugar from sugarcane, and from crude oil to that value-added products, and from limestone and clay to cement. These we are making the product through set of stages, sequential steps, and then can make a final product. So this we call it as a process in chemical industries. So the conversion, say for example, sugar from sugarcane and the crude oil from LPG, all these are not directly coming. So we are doing through a set of process. But before the process, so there will be certain research how the sugarcane can be converted into a sugar crystal, like how the seawater is getting into a crystal salt. So there will be some research used to happen during that initial stage, starting stage. So based on that, we will be proceeding for the industrial production. So this research process or or a company make the process with a licensing tool, with a developed licensing tool where they sell it to the investor. If someone want to go for a sugarcane industry, go for investing in a petrochemical plant or cement production, so they no need to go for the thing for the new thing. Already the process is developed and the technology is made, so they can directly go on buy the technology from them and then ask them for for the implementation of the industry. So this technology is produced through different research activities, and then they sell their technology for a certain cost for a certain lifetime. So open the technologies are with like open art, and then the licensed technologies we have two. So these licensed technologies are what we have discussed, and open art is like a simple process. So if you want to invest with a huge amount, so generally people will go with the licensed technology. So no one will go for take a risk. So after implementing a plant, after construction of the plant, so if the product I am not getting with the required spec, then the entire investment will be a waste. So then generally people will go to a licensed technologies. Okay, next, few people are recently passed out students. So we in chemical engineering, there are basics to operations, unit operations and unit process. So unit operation involve like the transfer of fluids, and then the heat transfer and the mass transfer. So these are all the fundamentals for the process design, where the fluid transfer is happened due to the pressure drop, differential pressure, which involves a pump or a compressor. And for the heat transfer, for the transfer of energy, it is due to the temperature difference, where we can increase the temperature of a fluid or decrease the temperature of a fluid, or we can convert the liquid to a vapor through heat transfer. And mass transfer is through a concentration difference, where the examples are distillation, absorption. And unit process is a chemical change where reactions are involved. So generally, all the technology, all the catalytic and non-catalytic, generally catalytic reactions will be used in most of the industries, where it involves it involves some technology. So there we need to buy the technology from the licensor. So for the guarantee for the reaction, and then to meet the required spec. So in industrial process, so there will be a to convert a product into to convert a raw material into a product. So there will be a certain stages. So in the stages, so the raw material will be prepared for the reaction. So you can see raw material and feed preparation and reaction and the energy recovery and product separation and final products. So say, for example, if I have a chemical reaction with a process parameter like 360-degree temperature, my reaction temperature is 360 degrees centigrade and my pressure required for the reaction is 70 bar gauge. So I need to prepare the feed for this particular temperature and then the pressure. So I will heat my feed to a certain temperature so that it will reach 360 degrees centigrade at the reactor inlet, and then the pressure will be around 70 bar gauge. So to achieve this, I will be putting my I will be heating my raw material to through different heat exchangers or furnace. And for the pressure, I will be using pump for the liquid and for the gas compressor to meet the reaction conditions. So once my reaction is over, so there will be byproducts in the reactions. So I need to remove the byproducts, and since we have heated, say considering exothermic reaction, so we will be having a higher temperature than the reaction condition. So in that case, we need to recover the heat energy, so which is not required for the final product. So final product will be almost will be the ambient temperature or to the required temperature for the downstream unit. So we need to recover the excess heat energy which is in the reaction products and then the byproducts. So the heat energy will be removed, and then through this one production of steam, and then the steam will be utilized for power generation or any other utilities for turbine and running and all. And for the product separation, they will be having a main product and then the byproducts. So those products will be separated through different equipments like separators or through distillation column. So and then the final product will be delivered to the downstream unit or to the end user. These are the major steps which we used to study in the literatures for different productions. So we'll be mainly focusing, talking related to oil and gas only in this training. So in hydrocarbon sector, so we have three streams: upstream, midstream, and downstream. Upstream is the exploration of oil and gas. So where we explore the oil and gas from the earth and then make it to useful feed to the downstream units, where they make the product like diesel, petrol, LPG. So we'll be giving in the upstream, we'll be giving the feed to the refinery or the petrochemical, where they convert the raw material to the value-added products. So in the refinery, we used to convert the crude oil to different lighter products like LPG, diesel, kerosene, naphtha, and then heavy oils. And then these products will be further processed to make further value-added products for the petrochemical units, and then the heavier from the crude oil will be again further processed to make the further lighter products, lighter value-added products. So these are all the midstream sections, and the petrochemical is the downstream sections. That means the product from the refinery will be placed as a feed to the petrochemical units like methane, ethane. So, and then this further will be processed, and then this will be made as a like a polypropylene and polyethylene. Further, that the end users are like end products are the plastic products. And the fertilizer and chemical industries also there, and there are many industries we have listed only related to oil and gas and fertilizer. So the raw materials from the refinery and then the petrochemicals will be utilized, and even from the oil and gas. So where they produce ammonia, and then from ammonia they produce urea for the fertilizers. And then the byproducts from these units will be going for a further for two different industries based on their this one market value, and then the market demand. So this is a overall schematic for a hydrocarbon cycle. So the first, this is a schematic block diagram. So the first oil and gas, oil or gas will be taken from the well through exploration. So there are different wells like oil wells or gas wells or a combination of oil and gas. So they take the gas naturally. The gas, if only gas is explored, then the gas will be sent to a treatment plant, gas plant, for the before sending it to the final user. So in the gas, there will be a separation, like there may be a mixture of gases like the process, that means the methane and ethane and some other heavier gases. Along with that, the impurities will be there. So the impurities we need to remove and then process the required gas to, and then supply to the necessary user. And then the toxic gases will be sent to acid gas treating units, like toxic gases means H2S and acid gas CO2. These will be separated from the gas. So, and then it will be treated, and then it will be sent the acetyl gas, and then the H2S will be converted into sulfur product. And then the main gas, natural gas, will be supplied to this one LNG facility. So or they can directly use it through gas pipeline for this one natural gas product, where they use it for this one fuel for industry, and fuel for this one domestic consumption uses. And the oil collected from the wells will be sent to oil production processing, where they remove the unwanted materials, like oil will be coming along with the water, and then the trapped gases. So we need only we need to separate the crude oil to send to the refinery. So the other unwanted components will be separated in the oil processing unit. So water will be separated, and then the gas will be separated through set of operations, and then only the crude oil will be supplied to the refinery through storage tanks, through pipelines. And then the water will be treated, and then the treated water will be disposed as per the local government regulations. Then the crude oil will be further sent to oil refinery to make value-added products, lighter ends. And then the lighter ends are like LPG, naphtha, and then some other feedstock to the some other industries like fertilizer industries for manufacturing of this one ammonia. And the LPG, we know LPG, gasoline, jet fuel, kerosene. These are all the domestic users and then the vehicle users. Then the bottom portions will be used for just one lube oil, and then bitumen for road making purpose, and then then further downstream it will be processed in downstream, and then it will the final the waste will be toxic waste will be converted into sulfur. Toxic waste here we tell we are speaking is hydrogen sulfide. This is a simple block diagram. And process engineering. So what we do in the engineering company. So here still we have till now we have talked related to this one theoretical from the subject. And now what we are going to do in the industry. So this is the process engineering. So in the process engineering, so to start making to start with the raw material to product. So first we need to do these steps like concept study, feasibility study, feed. They used to call feed, front-end engineering design, and basic engineering package, and then the detail engineering design, which is the next process for the final this one green signal for the this one construction of the plant. So in the concept study is like say I want to make a plastic. So how can I make a plastic? So I can make a plastic from ethane or methane or the propane, like that. So that how that it will be converted into plastic. Methane is a gas. So that gas will be going for a certain reaction, and finally it will be that converted to solid product. So this study will be conducted through some research study, laboratory study. So, and then they will come to a conclusion. Okay, like we can make a plastic from a ethane gas or propane gas. So like this. So there will be a concept study. So I am speaking the familiar products. So similarly, anything can be we can put it in the concept study before going for a large production. And then from the concept study, so whether it is feasible to this one to make it in a commercial product. So that study will be conducted through a feasibility study. So I hope you people visited any industrial visit. So can you people name what are the industries you have visited? You can put in chat box. Speak CPCL. MFL Vizag. Speak Vizag. PNC. Okay, you can stop. So most of the people are mentioned where it is, whatever the industries you have mentioned, so all are almost near to the coastal area, right? CPCL, ONGC, Kothari is in Chennai. Leave that sugar industry, and ONGC, Chennai. So most of the industries are in coastal area, right? So where the why it is coastal area selected? So Vizag, we have one refinery. In Mangalore, we have refinery. In Cochin, we have refinery. In Chennai, CPCL, we have refinery. So we get the raw material through ships, right? So from the Middle East, we get the crude oil. Majority of the crude oils are coming from the Middle East. So we get raw material. Okay, so and one more thing. So we have refineries in Assam also. Assam. So how they get the raw material? So you can put in chat box. So there, they in Assam they do oil exploration because Assam has oil field, and Okay, so one more question. So we have refinery in Punjab, Mathura, that means in UP, and we have petrochemical plant in UP, Kanpur. So for a petrochemical plant, we need gas, and for refinery, we need crude oil. So it is the refinery is there in Punjab and in Mathura. Mathura means in UP and in Bihar. So how they get the raw materials, crude oil? They don't have that this one like Assam. Yes, through pipelines. So for petrochemicals, it will be from other refineries. So we have petrochemical plant in UP. So some majority of the raw material is going from Gujarat through pipelines to the to UP. And refinery in Punjab is getting oil through pipelines through from Gujarat. Gujarat is having a vast seashore. And Mathura. And we have all these places are well connected by railways also. So we used to hear that goods train. So oil will also be shifted through the this one train. Crude oil will also be shifted through trains to these areas. So why these industries are kept in Punjab and Mathura? So and in UP, that is the it is purely a petrochemical plant. So where it is getting the major source of raw material from Gujarat through pipelines, and maybe from other industry, local industries also. So these things are studied through whether we can put the industry there in Punjab. All these things are studied through feasibility study. So they will see the different factors like environmental factor, then government local regulations, and then the land availability, and then the ambient conditions, and then the people should be available for there for the work, and then local people should support for the industry, and then the development for the local area. So all these things will be studied, and then government will give permission for these industries. All these things are getting studied through this feasibility study. Whether it is feasible to put the industry in Punjab, and then they need to make the profit also, right? So through the feasibility study, these things will be studied, and then finally given to, as a report. And then the next stage is the feed, front-end engineering design. So if I want to, if say you can take Reliance as an example. Reliance is having refinery in Jamnagar. So if Reliance want to put a refinery in Madhya Pradesh, so they need some idea, right? So how much cost will be required for the refinery? They will go to a engineering. They will go to a licensor company. They will ask for these details. We have a plan for a refinery because they know the demand. They know the market demand. They are already in the market. They if they have a huge demand, which exceeding their this one inside refinery capacity, which is in Jamnagar. So they will look for some other area, and then they will plan for a this one study. That means concept already done, feasibility already done. They will go for a feed stage. Feed stage means how much budget will be required, and how much capacity they can put, how much area is required, everything. So they will go for a front-end engineering design. So what they do, they will go for a company like UOP or KBR or universal companies, where they are having this one huge experience. So they will go and then that feed, after the feed study, they will come to know how many equipments are required. So those things will be seeing in the next. So they will come to know this many areas required for putting the plant, and this many metal is required for putting the plant, and this many water is required for the plant, and this many storage areas required for the storing the raw material, and this many storage areas required for the storing the products, and they will give the overall estimate. For this, for putting the refinery in Madhya Pradesh, we need 50,000 crores like that. And then they will say, for example, there will be huge equipments involved. So they will also get estimate with including all. So the front-end feed, front-end engineering design, which is called as a feed, and then the basic engineering, both will be combined and given as a package to the owner. That means to the Reliance. Which basic engineering package will be having additional documents along with the feed. So once Reliance agreed to go for a, okay, we can 50,000 crore, okay, we can go for putting this one refinery there. Then this basic engineering, that feed package will be given to a detail engineering company. So detail engineering company, there are many companies like Bechtel, Petrofac. The detail engineering, we call it as like EPC companies, engineering, procurement, and construction, where they do complete work from the feed data till the commissioning and operation of the plant. So in this detail engineering is a major part of the work, where all the most of the chemical engineers will be, many chemical engineers will be working there. So in concept study, feed, feasibility study, feed, BP, the requirement of engineers will be less. So in detail engineering design, there will be a huge, there will be multidiscipline work with more number of chemical engineers. We call it as a process engineers. So detail engineering design is the main work, which is the major work for putting a plant. So this concept study, feasibility study, feed, after feed, that the feed data will be given to different engineering concerned EPC contractors. So who are giving a low code, so they will be low code with a reputed company, like those will be awarded the detail engineering contract for this one. And in detail engineering, so the activities, what the process engineer need to do. So we have a process simulation. So for example, since the crude oil, so we need to start with the crude oil. No, the engineer will start with the crude oil. So we will do the calculation. He will do the different sizing for the equipment, all those things. So all those things we cannot do through a manual calculation. So we need some software. So simulation software, because the components involved are like a complex component. It's not like a simple like water or a pure component like a methanol, ethanol, like that. So the components involved are complex components. So which the calculation through manual calculation or Excel 2 is difficult, or it will take more time. So so all those things are put in a software package called as simulation. So even you people might have studied in colleges. So you can name any simulation software you worked in your college or in your college exercise. As when I'm saying, okay. Okay, so Aspen generally this STRI ChemCAD, okay, Honeywell. Aspen. Okay, the known companies are this one. This Honeywell, Unisim is there, and then Aspen ICs is there. These are the known companies, and then Aspen Plus. Okay, enough. STRI, okay. So process simulation is required for process simulation is required. Say for example, okay, we can stop this one answering. So process simulation is required as a first step in feed or in detail engineering activity. So generally all this activity will be done in the feed, and then that simulation output will be given to the engineering company. So the engineering company start with validating that simulation data. So they will start with the simulation again. So they will start the HMB data, heat and flow mass. So some of the things may be new to you. So in the later training session, you may be able to know. So the design start with the simulation. So simulation where it involves, like say for example, we talked about the distillation, right? Crude oil will be put in a distillation column, and then from the distillation column, the top LPG will come, or natural gas will come, and then the LPG, and then kerosene, diesel, and all. So we just see it as like a process in one distillation column. But when you go for a design, we don't know how many trays will be required, what is the temperature required, all those things. So those things will be preliminarily done in the simulation, and then we need to reduce the temperature, increase the temperature. So we need to put a heat exchanger. We need to pump the liquid from one place to another place, from the bottom to the top. We need to cool the liquid from one place to another one tray to another tray. So all these things we'll be knowing through, we'll be come to know whether heat exchanger is required or not, or the pump is required or not, whether cooling is required or not, through the simulation. So the simulation activity is this dedicated activity where it involves these steps, like freezing all the equipments. What are the equipments required for achieving my this one to get the desired products? Say for example, I will tell one product, say ammonia. So what are the raw materials required for ammonia? Okay. Ammonia is NH3, right? Which is nitrogen plus hydrogen. So you can put in checks what are the raw materials required for ammonia. Hydrogen and nitrogen. Okay. Hydrogen, nitrogen required. By through the formula we come to know. Okay, nitrogen, hydrogen. We need nitrogen and hydrogen. So what is the source for nitrogen? What is the source for hydrogen? So source for nitrogen is here. Okay, and then for hydrogen. So okay, so we know two raw materials are required. So hydrogen is not a direct product. So we need hydrogen through some process. So say naphtha. So naphtha is there. So naphtha through some process, it will produce hydrogen. Okay. So I know that I need raw material nitrogen and hydrogen. So hydrogen we cannot produce. We cannot have it direct. So we need to go for a hydrogen manufacturing unit. Okay. So for that, one of the raw materials naphtha, steam reforming. Okay, so we will start with the naphtha. In the simulation we need to start with the air and then naphtha. So for nitrogen we will not get directly from air, right? We need to separate the oxygen, right? So we need to go for we need to take the air and then go for a separate process for removing the nitrogen from atmospheric air, right? So for that, it will be going for a certain process. Yeah, cold box. So through the low temperature process, nitrogen will be achieved, and then through some reforming process, we will get hydrogen or some other process. There are different processes for manufacturing hydrogen. We'll get the hydrogen. So from hydrogen, we'll get the hydrogen from. So finally we get a nitrogen and hydrogen as individual, and then we will put this in a reactor and then make it as a ammonia, NH3. Okay. So in between there will be many equipments, right? Say for an air to nitrogen, we need a compressor, we need a refrigeration system, And for naphtha to hydrogen, we need a reforming where it involves catalytic process. And finally, the purifying unit will be there, that PSA, pressure swing absorption process is there. And then finally, we get hydrogen. So we need some equipment right in between, like a exchanger will be there, heating will be there, cooling will be there, compressor will be there, pump will be there. So all those things will be put in the simulation in a sequential manner. And then finally, we'll get ammonia, right? So where the ammonia will be used? Ammonia will be used for urea manufacturing. So urea, again, this will be further going for next simulation for the production of urea. So before, okay, so this is the simulation. This is the process for simulation. So how we need to arrive the final product through set of process. So we will put all the equipments and we'll be knowing the capacity. Like I need to produce this much 10,000 tons of urea per day. So for 10,000 tons of urea per day, so what is my air required quantity? What is my naphtha required quantity? So all those things we'll be putting it in the simulation at the start. And in each stream means in each equipment inlet, outlet, we will be getting the required quantity. So I need I will be taking, so for example, what is the nitrogen percentage in air? For 1 ton of, for 1 mole of nitrogen, I need to remove the oxygen, right? So I need to take the air, I need to remove the 1/3. Right, 1/3 is the nitrogen, right? So I need to remove that 1/3 oxygen from the air, right? So similarly, from the naphtha is like a hydrocarbon. I need only the hydrogen, right? So I need to remove the other components. So all these things will be put in the simulation. In each equipment, we will be removing different components. So finally, we will achieve the hydrogen. So I need to produce 1 ton of hydrogen. How much quantity of naphtha is required? So to produce 1 ton of nitrogen, how much quantity of air is required? To produce 10,000 tons of urea, how much quantity of ammonia is required? So all these things will be doing through the simulation. So if we go for a manual calculation, it will be we can go for a rough calculation. But equipment wise, inlet, how much quantity will be there? How much inlet, outlet quantity will be there in the outlet? What will be the temperature? What is the pressure required? So all those things will be calculated through the simulation. So from the simulation, we'll be taking the process flow diagram. Process flow diagram means what we talk, like what are the equipments required in between in making the urea, in between from the raw material to the end product. So the process flow diagram will be having different equipments used for the conversion of raw material to the product. And then the same from the simulation, we'll be taking the heat and mass balance. Heat and mass balance, whatever the data we talk, we'll be extracting the data from in each equipment. What will be the inlet composition? What will be the inlet temperature? What will be the inlet pressure? What will be the outlet process condition? How much quantity will be vaporized? How much quantity will be going through liquid? All those data will be taken through the heat and mass balance data. And then with this data, we will be doing the calculation. We will be for producing this much of say 1 ton of ammonia. So how much what is my line size required for the air? We will be taking the air right from the atmosphere. So we'll be taking air through duct or the piping section will be through the duct, and then we'll be compressing it through and then putting it through a pipeline. Right. So we'll need to give the size for the pipe, right? And then we need to go give a size for we need to size some equipment, like we should have a compressor here. So what will be the compressor capacity required? And what is the line size required? And so those things we do through the calculations from the heat and mass balance data. And how much the heat and mass balance data will give the utility requirements, like how much is the cooling water required, how much is the heating media required. Heating media means it may be a steam or it may be a furnace to heat the content. And here we have, in case of ammonia, there will be like a refrigeration system will be there. So we'll be taking the data from heat and mass balance and then doing the calculations. There will be different calculations, like for the. So those will be discussed in the later stage. And then the piping and instrumentation diagram. So piping and instrumentation diagram is the next stage of the PFD. So we'll be putting the, like, I need a compressor, I need a pump, I need a separator, I need a distillation column, like that. How this will be connected? How this will be connected? So this will be connected through piping or duct. And then what are the equipments required? And then so all this data, all these drawings will be put in a pictorial representation with the complete details. Like, means the pipe means we will be putting the pipe size. And what are all the instruments required? Say, for example, we can say any process equipment. Any process equipment, you can say any process equipment. Put in chat. Any process equipment, say some vessel, something. What do you know? Pump. Okay, next. Distillation column. Next. Heat exchanger, reactor. Next. Okay, FCC condenser. Okay. Pump. Okay, what you will measure in pump? What you will measure in pump? What you will measure in a reactor? What you will measure in a exchanger? Heat, flow rate, temperature, pressure. Yeah. So industry. So in industry, chemical industry, we measure flow, pressure, temperature, level. Level means in case of a vessel or a tank. So all these things will be, yeah. So all this will be through a instrument. Pressure means through a pressure gauge or pressure transmitter. Temperature means through a temperature gauge. Gauge will is like a physical instrument, and then the transmitter will be a digital instrument. So temperature, pressure, flow rate, level. Okay. And if any composition is required, then composition analysis will be there. Okay, so these things, what are the instrument required? So those things will be captured in the P&ID, piping and instrumentation diagram, for a equipment. So whatever you people have mentioned here. And then the control, say for example, for a heat exchanger, we will be measuring the temperature, right? If the temperature is going high, so what you will do? So we need to decrease the heat input, right? So we need to put the control for the temperature. And if the pressure is going high means, so we will be decreasing the source for the pressure. It may be through compressor, or we will be venting the excess pressure. So we need a controller, right? Pressure controller, temperature controller. So these things will be finalized in the simulation itself, finalized through in the PFD, second process flow diagram. Whether for the distillation column, for the heat exchanger, what are the controls required? Temperature control, pressure control, all those things will be fixed in this process flow diagram itself. So in the piping and instrumentation diagram, we will be going in detail. So this piping, we will be doing the calculations. All those calculated data will be put in the piping and instrumentation diagram. So in this, we call it as P&ID. So this P&ID is the master and mother drawing for the entire stage of the project. That means from the design stage till the construction, and then the commissioning, and then the plant team who is handling the plant, who is operating the plant. And then after the plant run for 2 years, 3 years, they will go for a shutdown. So at that time, after that time, they will refer this P&ID. So this P&ID is the mother drawing for the this one, for the whole project, and then the whole unit. So where it covers all the piping, and then the equipment, and then the instrument, all the things, whatever there in the site. So this, after the design stage, actually this will be the input to the other discipline. So other discipline, and finally through the P&ID only, we can go to a site and then see, check what are the equipments available or installed. Those things for checking, we will be taking this P&ID to the site. And then the next equipment data sheet. So once we will be making the P&ID, and then we will be for the next stage, we need to buy the equipment, or we need to buy the pumps or compressor, whatever the equipment we defined. So we need to buy those things, right? So how we will buy? So we cannot go and buy in the market. So we cannot buy like a standard like a household item. So we need to give our specification. I need this much capacity of pump. So I need 10,000 meter cube per hour. 1,000 meter cube per hour for a pump, and then the discharge pressure. My differential head is say 80 bar gauge. So I need to give all my process condition to in the equipment data sheet for a this one for a procurement. So we need to make a process data. Say for example, for the pump, what are the process data required for the pump? You can put in chat box. NPSH. Okay, next. NPSH head. Okay, NPSH flow rate. Okay. Okay. So this is enough. Okay. So all those things are required. So all those things we will do a calculation for the NPSH. We will do a calculation for the differential head, and then we will finally we need to give this data to the vendor, right? So we'll give the data to the vendor to the manufacturer through this data sheet. So this data sheet will be filling our giving our all the process data in the data sheet, and then the equipment owner will be the mechanical engineers. So we, the chemical engineer, fill our process data, and then the equipment owner will be the mechanical engineers. So in the same engineering company. So they will take care of the next steps. They will give it to the this one different vendors, get the quotation for the this one for the required data, and then it will go for bidding, and finally it will be awarded some vendor, and then they will go for a this one manufacturing of that particular pump, that vendor company. So once we give our process data till the that equipment arrived at site, so we will be cross-checking. The processing will be cross-checking in between different stages before giving before giving final this an offer to the vendor. So what the vendor is giving is matching our requirement or not. Those things we will be process engineer will be checking. Similarly, instrument data sheet. So instrument data sheet, say for example, take a temperature. So my operating temperature is 360 degree. So I need to buy an instrument. So what will be the temperature I will be asking to the vendor? So you can put in chat box. My operating temperature is 360 degree. So I need to buy a temperature instrument. My operating temperature is 360 degrees centigrade. So what temperature I can put ask for the vendor? Okay, 400, 375. Okay. So we will have some margin, right? So we will have some margin. Okay. And we can ask for like say 400. So for this, for whatever we are talking, so all these things will be through. We'll be having a proper guidance through certain documents. So that we'll be seeing the next slide. So we cannot go and ask for to the vendor to 600 degrees centigrade. So if we ask for 600, where we will not be seeing that much temperature, then we'll be buying a costlier equipment transmitter, right? Instrument. The cost will be more if we ask for a 600. So we'll be asking say 400 or 420 like that. So how to choose these things will be guided for each project. So there will be certain documents which we need to follow for this. So process team will be giving the data to the this one instrument engineers. Instrument owner will be the instrument engineers. So we'll be process engineers will be giving the data to the instrument engineers. So in the data sheet, so we'll fill our process data. Say for example, for a temperature, and there will be like pressure. We need to buy pressure instrument and level instrument. Okay. And next is equipment list. Equipment list is a consolidated list of all the equipments which we talked in the process flow diagram. With further detail means it's a consolidated list. Let's say for example pump. So we'll mention in the equipment list we'll put pump. This project is having this many pumps with this many capacities, this many differential head, and this many size. And equipment list, we will fill our process data, and then the equipment list owner will be again the mechanical engineers. And then the line list. So the industry will be, if you see, go to any process industry, we can see big equipments. So how all this will be connected? How all the equipments will be connected? Can put in chat box. So how the equipments are connected? How your household kitchen is connected with water? Pipelines, pipelines. Okay, piping. Okay. So similarly in industry, we need to transport the fluid from one place to another place, either it may be gas or liquid. So okay, the industry involves a huge requirement, huge pipings will be there. And even if you go to a piping, you might have visited the industrial visits. So you can see a lot of racks will be there where it will be carrying there. There will be a lot of pipelines which will be carrying hydrocarbons, utilities, instrument air, nitrogen, cooling water, steam, etc. So from the P&ID, point number 5, from the P&ID, so we will be making a line list, piping list. So P&ID will be showing equipment to equipment will be connected through piping with the details like from which equipment to which equipment, and the piping details like line size, and then the pressure rating, and then the piping MOC, whether it is a carbon steel or a stainless steel. So all those details will be listed in the line list. So this will be utilized for the this one. This is the completely process deliverable, which will be utilized for the subsequent this one in the utilized in the subsequent stages by different disciplines. So we'll be seeing in detail in the next slides. And then the package specification. Say for example, so we are talking the main about the core process, right? Say for example, in a plant there will be a waste treatment, right? Say assume a wastewater treatment. So in the plant there will be a different wastewater generator, right? So the main company, say assume Bechtel is doing a detail engineering. Okay, they are master in core hydrocarbon. Okay, and then there are certain process where there will be a specialized package vendors are there, so they will be doing better than the engineering companies. So what they do, they upload this treatment package, water treatment unit to a different vendor, different licensor or the different company. So they will give the spec to that particular company. These many 10,000 meter cube per hour of wastewater will be coming from my this one industry. From my from say for example you have 10 units, so from 10 units. So and then with some spec, oil spec, and then they will give the spec. This is the wastewater spec, and then you need to discharge to the atmosphere. Atmosphere in the means they will have a local plant with the government spec. Government will define the spec. What should be the spec for the this one wastewater discharge to the atmosphere. So for that spec, they will design and then produce, give the complete package, complete unit, and then put it in the refinery. Say for example, if they are going for refinery. So and similarly, the water required for the process plant. So refinery and all requiring a huge water requirement, right? So how they can get? They cannot take underground water. So they need to take, generally they take water from the seawater. Seawater, they will take the seawater and then put a different evaporator. Like these also like licensing companies are there. They'll make a final clean water through different technologies. So this also will be awarded to different companies. So they will tell I need 20,000 meter cube per hour of this one DM water. DM water means demineralized water for my this one production unit. So they will give this specification and they will give the seawater specification. So that particular licensing, that other package company will do all the complete design and then they will install those things in the refinery. And then the cause and effect diagram. So cause and effect diagram is like, say we are all doing these many activities, right? So we need to see if something goes wrong, we need to stop that activity, right? We are pumping some fluid in the equipment. We are putting a compressed gas in some equipment, right? So can you mention any? So hope you people are staying in some apartments. Apartment, there will be overhead tank, right? So overhead tank. So how the overhead tank is filled? Through some tanker or through underground water, right? So from underground water, so it will be pumped through a pump in the ground floor, and then it will be pumped to the overhead tank, right? So when the overhead tank fills, how you will go and stop the water, the pump? You can put in chat box. In olden days, the water will overflow and then it will come to through this overflow pipe, and then it will be coming to some visible area. Then people will come to know, okay, the tank is filled, we need to go and stop the pump. Right? Nowadays in apartments, we no need to that convention system is also there. And then there is one digital system is there in the apartments. So in the water tank, they put some sensors, level sensors. Once the level reaches high, it will go and stop the pump. It will give signal to the this one to stop the pump electronically. No need to go and this one manually go and stop the switch. Hope you people have seen this in your apartments. You can check. There will be a box in the small box in the near to the pump motor, small box where they connect this control system. Because nowadays people are busy. If someone switch on the pump for this and water, and then they will leave unattended, and then the water will be overflowing and then going. Right? So similarly, so in industry, so if we take an atmospheric tank, so we are filling atmospheric tank, say we are filling crude oil, or we are filling some, my finished product is my petrol from the refinery. I am filling it into a storage tank. Okay, so if my level, the storage tank will be having some level, right? Level instrument will be there, right? So if the level goes high, then what I need to do? What the system need to do? What we need to do? You can put in chat box. We are filling a petrol. Even you people are filling petrol in bike, right? So if the level reaches, what happens? It automatically cuts, right? In the petrol when we are fueling our bikes. Yeah, we'll give set point and then it will automatically stop. If we have some inlet valve, then we'll close the inlet valve. Okay, my tank is filled, you close the valve. Or we can close also the incoming source. If we have multiple users, we can close the inlet valve. If we have only one user, we can go and directly stop the pump. Okay, enough, stop. Level is achieved. Okay. Okay, so these things we are telling simply for the level, right? Similarly, so in a reaction, in exothermic reaction, so in my reaction temperature is 360. Okay, so even for an exothermic reaction, so if I cross 360.5, it is very danger. It will lead to runaway reaction. Okay, so in this case, what I need to maintain, what I need to do in this temperature case. So I have a temperature of 360. So I have a controlled process temperature up to 4. My reaction, if it is exothermic, my reaction temperature will go up to 400. Okay, 400. So if it goes beyond, then it is a runaway reaction. The reaction is not with us. the temperature will shoot, and then it will reach 400, 600, it will reach beyond the instrument range. We don't know what is the temperature then. So in that case, what I need to do? You can put in chat box. Temperature control, cooling water, okay. Okay, so I need to control the inlet temperature, right? So if it is exceeded, so I need to control the inlet temperature, right? So I need to, I will have some furnace in the inlet for the temperature, increasing the temperature. And then if my control, if that control failed, okay, if the control failed, what I need to do? I need to stop the furnace, right? Or if my temperature is exceeded, another time, if my outlet temperature is exceeding 400, so we need to stop the process, right? Otherwise, what will happen? If the temperature goes beyond, say, my temperature measuring capacity will be up to 450, say 450. If it goes beyond, I don't know what is the temperature. Say for a metal, say for a carbon steel, if it goes beyond 560, it will be red dot. Then we will be, then it will be then bleed condition will happen. Then if the temperature exceeds beyond our control, right? So in that case, I need to stop my heating source. I try to control. If I am not able to control, I need to stop my heating source, right? So these things will be considered in the cause and effect. So these also we need to put in these also the process engineer work, which we mention all these things in the piping and instrumentation diagram. So this we by default we do, the process engineer will do. And then it will be subject to the next subsequent discipline. Safety team will be there, HAZOP will be there, so hazard will be there. So those things will be questioning on our design. And then if further safeguarding is required, then we'll be adding further interlocks. So there will be a cost. The cost will be like increase in temperature, increase in level. And then what will be the effect? Effect means I need to, if my temperature is increasing, that means beyond my control, I need to stop my furnace. I need to stop my pump, like that. Okay. So all these things will be captured in the P&ID, process and instrumentation diagram. And the example we'll show in the later stage. We'll move to the next slide. Okay. Next, design documents. Design documents. So when we are going for a design, detail engineering, when we before starting our calculation, simulation, everything, so we need to go through the design basis. Design basis will be given by the client and then the licensor, along with the licensor, in consultation with the licensor, who provide the feed package. So say for example, there will be 10-15 units in a refinery. So all this will be done by an engineering company, detail engineering company. That means one person will not do all the design, right? One plant. So there will be 10 teams. 10 team who will be doing different design for each plant. So each team will be doing. So all of them can take their own values, and then they can take their own margins. So to avoid that different, so the design basis will be covering certain parameters which everyone need to follow, which will be provided by the licensor and then the client, in consult with the client. And those things we need to follow. The design basis will be consisting of like the environmental conditions, like if it is in Madhya Pradesh, what is the environmental condition there, what is the cyclone, like they will take the 100-year data and then provide all those details for the environmental condition, like any cyclone used to happen, like how many years the cyclone used to come, or in how many years flood used to come in that area, flooding. Those details. And then what is the maximum ambient temperature, what is the maximum lower atmospheric temperature, all those things will be given in the design basis. And then for the design of your equipment lines, all those things, calculations, all those things, you will be given with the criteria. For a line size, you will be given with velocity. For equipment, you will be given with the inlet momentum. And you will be, for a tank, you will be given with the height. You cannot go beyond this height. So there are many parameters which is required for your calculations. You cannot assume your own. We need to follow the design basis, what is given in the design basis. Design basis will be prepared with the help of different standards. Different standard in the sense for this one, like API standards are there. And design basis is for applicable for all disciplines, process, piping, instrument. So all the team need to follow the design basis. And then the philosophies will be generated at the initial stage of the project, which we need to work. Say operating and control philosophy, which we talked, like how the temperature need to control, how the operation need to do. All those things will be given in the operating and control philosophy. Like we say control philosophy in the sense here we can how we can reduce the flow. So the pump is pumping a fluid from one place to another place. So I want to reduce a flow. How can we reduce the flow? I will put a control valve, I can reduce, right? So you can put in chat. I can put a valve and I can reduce, right? Or any other method? Or I can reduce the speed of the pump, right? If it is a VFD pump, I can reduce the speed of the pump, right? Yeah, I can reduce the speed of the pump, right? Okay, so these things will be defined in the control philosophy. So this is my level, how I need to control. With one level controller, true controller, all those things will be captured in the design philosophy. Based on that, we need to work for our design. And isolation philosophy. So isolation philosophy in the sense in the industry, there will be standby equipments in the sense for rotary equipment, say for a pump, all the rotary equipment will go for a maintenance for a particular time, and the running time will be defined. This pump need to go for a maintenance for at least 1 year, or after 1 year, like that. So during that maintenance, so they will use a standby pump. That means if I need a 3 pump for the operation, I will be going with the 4 pump or 4 plus or 5 pump. So these things will be defined in the isolation So for maintenance, we need to go for isolation. So whether I need to go for a single isolation wall or 2 isolation wall for isolating a pump. So these things will be captured in the isolation philosophy. And for the drain, whether I need to go for a single isolation wall or double isolation for the drain. So all those things will be captured in the isolation philosophy. And there is a positive isolation also there. So that also captured in the isolation philosophy. And then blow down and depressurization. Why you need to depressurize a system? You can put in chat box. So the plant is the plant will be under pressure, right? Under pressure in the sense operating at not operating in ambient pressure. It will be operating pressure at 10 bar gauge, 20, 60, 70, 100 bar gauge. So why we need to depressurize, release the pressure? In case of fire, what will happen? You can put in chat box. You can put in chat. In case of fire, people might have heard boiling liquid vapor expansion. So in case of fire, so all are metal only, right? So all the metal will get the heat and then it will go to the next stage. That means it will soften and then finally it will go for a rupture. So with the pressurized content inside and then the hydrocarbon inside, then it will make an explosion and then it will add fuel to the existing fire. So in case of any pressure, any fire or any other emergency, any other plant emergency or any leak, major leak, then they need to depressurize the system through a proper channel. Depressure in the sense not to the open atmosphere, it will be a closed atmosphere. All those things will be captured in the blow down and depressurization philosophy. With this philosophy, we need to consider in the go for the design. Considering the design. And drain and venting philosophy that we talked. Drain means if it is a hydrocarbon, it will be a closed drain. No hydrocarbon will be put in an open drain. Like we in our household, we put our wastewater in an open drain sewage, right? So similarly, in the industry, only rainwater will be captured in separate drain, and then the process water with drain will be whatever it is not harm to ambient will be put in open drain, and then the rest all the hydrocarbon and then the process fluids will be put in a closed drain. And then similarly, the vent all the process gas will be vented through a closed venting system, where it will be finally vented safely through this one flare system. And then any steam system can be openly vented, steam system. And then safeguarding philosophy. Safeguarding philosophy in the sense, here we have talked about the interlocks, right? Similarly, there will be a mechanical, in case of overpressure, we will be having a transmitter, pressure transmitter. We will stop the system. If that fails, assume that if that pressure transmitter fails, so then we'll be having a mechanical device. So those things will be captured in the safeguarding philosophy, how we need to consider all those things. And then the process description. So process description will be giving, that means process engineering will be giving the process description for the process. Then the process simulation, and then the HMB report, heat and mass balance report. This will be extracting from the simulation and then using it for the calculation. These are the process documents. And process flow diagram, P&ID we talked. And various calculation reports. Whatever they do calculation, we will be making it as a report. So after the plant is commissioned, and then after 4 or 5 years, if the company wants to go for expansion, so in that case, they need to go through the documents. What is the existing design? So what they have considered in their calculation. So all those things they will verify, and then consider that as an input, and then go for the next revamp things, capacity expansion. So calculation reports are required. Whoever doing the process calculation will be making the report. So it is not like a one calculation, like I have only one line, I have only one vessel. There will be huge vessels in a refinery, huge vessel, huge number of vessels, and number of thousands of pumps and hundreds of compressors will be there in a refinery. So each plant will be having a dedicated report for the calculations. And then various lists, consolidated list like what are the fluids handled, what are the equipments we talked, and then the line list, and then the tie-in list. Tie-in list will be whatever the package we give it to some other vendor. So there we will give our tie-in. So this is my this one tie-in. Till here I will do, and from here you need to do, like that we will be communicating to the vendor. And these things will be represented in the P&ID, and then that for the entire unit there will be a list, consolidated list for this one easy identification, and for the subsequent discipline checks. And then the data sheets. Data sheet we talk to go for a procurement, we need a data sheet. We need to put our process data, and then the material team will put their material of construction data, and then the mechanical team would put their data, and then the civil team will put their foundation data. So all those things will be captured in the data sheets. And specialty items. Some specialty items means which we do not do calculations, and it will be like vendor specific. So the vendor will do their calculation, and it will be their vendor proprietary things, and then we will be just giving our spec. I need this. I have this much of this one feed spec, and then they will ask what are the product spec you need, raw materials, and the product spec. So those things we'll put in the data sheet, and then give it to them, and they will design specialty items. And then specification for packages, like packages in the sense compressor and fire details. Like pump means pump will have a like a pump we see in the household. We just see a pump. Pump will have its associated auxiliaries. Lubrication system will be there, and seal system will be there to avoid the leakages. And lubrication system, since it is a rotary, lubrication system will be there. So for a compressor, will also be having like the compressor will be having lubrication and seal system. So these will be considered as a packages, and then it will be completely supplied by the package vendor. Compressor means they will not provide only the compressor along with all the accessories to run the compressor safely. So this thing will put it as a specification, and then give it to the vendor. This is also like indirectly a data sheet. Then the cause and effect diagram is like a process document. And in the basis of design is a key input to the this one to start the design. So, and then this will be provided by the client along with the feed licensor, because client is also not like a master, right? Master in the process. So they will go with the licensor. Licensor might have done the feed. So along with their this one guidance and then the overall budget, they will go for this one basis of design. And then the basis of design, that facility, location, ownership, everything will be there. Ownership in the sense that land related thing. And then if any partnership is there in the company, like 1 or 2 more companies are there involving, let's say for example 10 units are there. So in 10 unit, 1 utility wastewater treatment plant will be there. So that will be owned by the same company or that by the licensor company. Those things will be put in that this one basis of design. And then the composition, flow rates, temperature, physical properties, all those things will be, that means the raw material. So when we go for a design, even for the feed company, so feed company need the input details, right, for the this one from the client. So those things will be put in the design basis. And then the required product spec. Product spec means ultimately we need to meet the product spec. Otherwise, the entire industry, if the industry is not meeting the product spec, then we need to stop the plant producing the product, because it ultimately they need to meet the product spec. Otherwise, there will be no demand. Then if it is not meeting the spec, then they will go to the licensor. And then they will again do some modification, and then they will achieve the required spec. And then the operating range, turn up, turn down, and flexibility. So operating range is, if I ask for a like production capacity of 10,000 meter cube per hour for a unit. So the design will be maybe 10%, 20% margin extra. So this will be provided by the client in the design basis. And then the turn down, how minimum I can operate the plant, how minimum capacity, say my operating capacity 10,000 meter cube per hour. So whether I can operate up to 1,000 meter cube per hour or 5,000 meter cube per hour. So these things will be provided by the the client. And then the flexibility. So I will be operating between this flow rate to this flow rate. So these things will be provided, and with all these things will be operating with operating range with the product spec achieved. And then the fifth one, the design criteria for the equipment and system. So who are doing a separator, so who are doing the line sizes, so they will be provided with the certain data from the standards. So we don't need to go our own. So we need to follow the criteria, whatever they're given in the design. So whatever the calculation we do, so everything will be provided, input will be provided by the input in the sense like what standard we need to follow, what range we need to take, certain constant values, all those things will be provided by the provided in the design criteria. And design life and provision for the future modification. Design life means how much is the lifetime for the plant, like say 20 years, 25 years, or 30 years. So based on this, the cost of the unit will be varying. So that means the design life, if they increase, that means then they need to put more cost on the this one material of construction. So they will consider for the corrosion allowance. Corrosion allowance they will consider, say for example 20 years. Accordingly, they will consider the corrosion allowance. So if they consider 30 years, then they will increase their corrosion allowance. Say for example, if the line is having 3 mm corrosion allowance, they will increase it to 5 mm, 6 mm, like that. And then the future modification. So they will go for a higher, say if I need only 10,000 meter cube per hour now, after 5 years, my demand is going to increase. So I need to provide a space for the future equipment. So accordingly, they will provide a future piping connections with the tie-ins, with isolation valves, and then the future space for the additional equipments. So those data will be given in the basis of design. And then source and conditions of utilities. Say source of the raw material will be given, like say for example refinery means they will be getting the raw material through the ship, and then it will be offloaded in the tank farm near the ship, and then from the tank farm, so it will be coming to the refinery tank farm, and the refinery tank farm, it will be going to different units. And the conditions of the utilities available. So condition of the utilities available, the major industries like refinery and all, they will produce their own power and then their own water. So if other small industries are there, then they need to get the power from other industries or other or from the government. And similarly, water. So small industries, they need to, if they don't have their own water, then they need to get from other industry or from the government, like city water. And the battery limits will be defined since we refineries having multiple units. So each units will be provided with the battery limits. So each unit will battery limit means who are working in that particular thing, they will not go beyond this one. That even for the design. So I am going doing the unit 1 means I will focus only for the unit 1. And the environmental conditions to that relevant to that local area, and then the government norms, all those things will be given in the basis of the design. And then the PFD, we also have a part of this one, PFD in this session. So PFD, which is basically extracted from the simulation study. So PFD will cover the basic equipment, major equipments, and then the line, major process connecting lines, and then the major controls also will be there in the will be considered in the PFD. From the simulation, we will be extracting all those things, and then the controls will be putting in the PFD. So for a heat exchanger, we need a temperature control. For a reactor, we need a temperature control. For a compressor system, separate system, we need a pressure control and level control, like that. And then PFD will be having shown with the additional SDVs and ESD. These are the emergency valves in case of any emergency, in case of any leak or fire in one unit. So they can easily isolate the plant with the help of this ESDs, emergency valves. For these valves, we no need to go. These are the automated valves. In case of any emergency, it is given instruction to this one, close the valves. So by that, thereby they will be isolating the source. And then PFD will be provided with the HMB. HMB, if the heat mass level is huge, then they will provide the numbers. If it is for a small plant or small process data is involved, means they will keep the data in the same PFD, in the same drawing. So generally, PFD will be provided with the stream numbers, and then for the number for that particular number will be going to a separate heat and mass balance table, where we'll be seeing all the properties of the particular stream, flow rate, temperature, and then the compositions. And then for the utility also, then the utility flow diagram is there similarly. So say we'll be having a heating, there will be a steam in the plant, and for cooling, there will be a cooling water will be there. For that, we'll be making a separate utility flow diagram, similar to the process flow diagram. And this is a typical process flow diagram. So where you can see, actually this is not eligible. So here we can see a separator here. One stream is coming and going to this vessel. And then one, this is 3-phase separator where I have shown the arrow. So you can see the stream number 2 is input to this vessel V0100. And then the vapor is going, that stream number 3 is the vapor going outlet. You can see that there is one valve shown with a small signal, that PC. This is the pressure controller for this vessel. If the pressure goes high, or this will maintain the pressure. If the pressure goes high, it will close the valve and maintain the pressure. If the pressure goes high, then it will open the valve and send down. And similarly, you can see that there is a level LC, and then going, and there is a valve in the stream number 4. So if the level going high or low, it will operate based on the level. So here in the if you see this 14, this actually this is a 3-phase separator. So gas is separated at the top, and then the water, and then the hydrocarbon will be separated in the chambers. Hydrocarbon in the right hand side, and then the left hand side is the water. So water is separated, and then it will be going to the downstream section. So there they will be having control. This is a schematic. So a typical PFS will be looking like this. So you can see there are multiple number of separators are there. So how we come to know? We can separate through only. I just need to separate the oil, water, and gas, right? We can make it in one step also, right? We can make it in one equipment also, right? So why they have gone for different 1, 2, 3? Because they cannot make it in one. So they need to go for a different separator. If they go for a one, then the size will be very huge. So to avoid that, they will go for a different separators with a different operating condition. So these things will be done through the simulation. And you can see there are some furnace shown here. So all these things will be done through simulation, and then from the simulation we'll be knowing, okay, I need this many separators for this process. Okay. And then the P&ID diagram. P&ID diagram we talked, and P&ID like piping and instrument diagram. This will be going as an input to the all other disciplines for the instrument, and then the mechanical, and then the piping, all the teams. So where P&ID will be covered with whatever the data you calculate, you will be putting those data in the P&ID. Like you will be calculating line size, that data will be put in the P&ID. What you will be putting the line with the, what is the line size, 4 inch, 6 inch, 10 inch, 12 inch, 14 inch, like that. And then you will be going for a relief valve calculation. You will be doing the relief valve calculation. You will be putting the relief valve size that will be shown in the P&ID. And what is the service in the particular line, and what is the unit number? There will be multiple units. So for that particular unit, what is the unit number? And then the sequence number. There will be n number of this one line numbers. So you'll be putting the line in sequence with some philosophy, numbering philosophy. And then the pipe specification, like what is the MOC and what is the pressure rating and all those things will be information will be put in the P&ID. And then the insulation for heat conservation, and then the personal protection, insulation type, and then the thickness will be mentioned in the P&ID. And then the instrument, whatever the instruments, and then the control, all those things will be put in the P&IDs. And then the alarm and trip settings systems are shown. Other detail like heat tracing, if heat tracing and spec break, if there is a heat tracing is to maintain the temperature. If say for example there will be a congealing service in a process pipeline, like if the temperature goes low, it will start solidification. It will start forming wax. Like you can see ghee in household item. We can see if you heat, then it will become liquid, and once you keep it in this one ambient temperature, then it will become solidified. You can see coconut oil. So similarly in industry pipelines, we need to maintain certain temperature. So if it goes beyond the lower temperature, then it will forming solid. So to avoid that, the heat tracing will be provided, because that fluid will be traveling through the pipeline to certain distance, right? So ultimately heat will be transferred due to the ambient conditions. So insulation will be there along with the heat tracing to maintain certain temperature, not in all the pipelines, wherever they're required. And spec break, where we are changing the MOC from stainless steel to carbon steel to stainless steel. Those things will be mentioned in the P&ID. And scope identification. Scope means if we are giving the detail to the package vendor, then we'll tell those information in the P&ID itself. This is up to this my scope, and then from here this is your vendor, that package vendor scope, like that. And slope details. Slope details means for a drain lines, the drain line should go towards the drain without any pockets. Pocket means no holdup should be there. So those details will be mentioned for the drain lines. And any specialty item is there, like we talk, like any vendor specific item is there, which we don't do any calculation. So those things will be mentioned in the this one P&IDs. And for P&ID, input records are like the PFD, and then the legend sheet. Legend sheet means like what are the, how a pump will be put in the symbol for the this one equipment, different equipments. And process philosophies like the isolation philosophies, and then the control philosophies, like whether I need to put one isolation valve or two isolation valve for isolating an equipment. All those things we need to consider from the philosophy for this one, making the P&ID. And piping material specification, which say that what is the pipe class, pressure rating, how much pressure it can withstand, and then the material of construction of that particular pipe. Those things will be given in the piping material specification. And material selection diagram. Material selection diagram means, say, you will be having a unit with a different material, like at one place carbon steel will be there, at some place stainless steel will be there. So those things you need to take input from the material selection diagram. So it will be done by the metallurgical team. And this is a typical P&ID where it shows where a separator is shown. You can see there are more number of data compared to the PFD, where we have shown only one equipment. It is a separator. So you can see level instrument is there. There are one level gauge is there, and level instrument is there. So from the level instrument, there is a controller, and then from the controller, it is going to another controller, and then from this controller, it is actually this controller is again the flow controller. The flow controller from this level as well as the flow, both signal it is going and operating this valve. So one will be master and one will be stave. So the P&ID will be showing in detail based on the control philosophy. And you can see one more controller is here. Here you can see here there is one flow transmitter, and then a level transmitter is there, and then the controller will be somewhere in the downstream. And you can see there is a relief valve. Relief valve means that pressure safety device, which is a mechanical device, which ultimately works if every automated system is failed. It's like a cooker in our, it's like a safety valve in our pressure cooker in the household. So if it is a steam, it will be open to atmosphere. That leaf will be open to atmosphere, and then if it is a process gas, it will be open. Put it in a closed venting system where it is safely discharged to the atmosphere through flaring system. And equipment list. So we'll be putting all the equipments in the plant with a consolidated list, like a number of type of equipment, like a separator or pump, compressor, all those things we'll put, and then the number of equipments, like this way pump. If it is a pump, then we will be having some 5 pumps, and 4 pumps will be working, and 1 pump will be standby, like that. And then equipment dimension, base dimensions. And then the pressure and temperature, operating the pressure and temperature, and then the design pressure and temperature, and then the material of construction, and then the power consumption for like a pump and compressors, or for like package units. And then the weight information. This is required for this one for transportation and for the this one civil team, where they work on the foundation and all. So this is equipment, typical equipment list, where we will put all the details. This is a consolidated sheet. We'll put the equipment number, quantity, description. So this list will be utilized by different departments for the next subsequent stages of the projects. Line list. There will be a number of lines in the plant. So we need to make that list, and then that will be useful for during the commissioning stages. So the line list will be provided with the line size, type of fluid, specification, insulation type and thickness, and then all the operating conditions, design conditions, and then the source and destination, from which equipment to which equipment is coming. Because we only process knows the in detail of the thing, other discipline may not know. So they need to go through that particular P&ID and then check, or the other construction contractor may not know the process. They just see this source and destination, and inside also they will follow that accordingly. And then the connecting P&ID numbers will be shown in the line list. And then the test and pressure medium. Once the line is fabricated in the site or in the workshop, then by what medium they need to test, like they use water for this one, testing the line, testing all the weld joints of the this one piping. And in some cases, if the volume of the pipe is very huge and that is in the site, then they will go for air. That means this is applicable only for a low pressure medium, like flare lines and all, where the line size is like 36. Very huge, line size will be huge, and we cannot use water as a medium for this one testing. So in that case, then they will use air or nitrogen with a very not nitrogen, air with a very low operating pressure, like low pressure, like 0.1 bar gauge. And if they use water, they will use 1.5 times of the design pressure for testing. So all this information will be mentioned in the line list. This is a typical line list where it shows the line size and then the spec from where to where, and then the insulation thickness, all those things. And cause and effect diagram, we discussed a compilation of, it is a compilation because in the plant we will have multiple equipments. So all those, for each and every equipment, there will be a safeguarding interlock will be there. In case of level high, what need to do? In case of temperature high, what need to do? In case of pressure high, what need to do? So all those things will be listed in the cause and effect diagram. You can see in the example, high liquid level in the storage tank is the cause. So what I need to do first, I will initiate an alarm. the level is going on, then what you do, the person who is sitting in the panel, the DCS panel, they used to control the level, try to reduce the level, what goes wrong, and then they used to reduce the level. And then if we cannot able to control, then it will automatically close the inlet valve. Similarly, if the low liquid level in the storage tank, so the liquid will be pumped from the storage tank, so which is a continuous process. In case of my liquid level is getting low or my incoming fluid is stopped, so the inventory will be getting emptied, right? So it will raise the alarm initially, and then finally it will trip. The pump cannot operate without a liquid. Okay, so if they operate without liquid means then the pump is gone. So to avoid that pump damage, so this trip is provided. So similarly, for different equipments, different things will be there, like what we talked for the reactor and then for the pressure vessel. So this is a typical cause and effect diagram. So here all the causes for the particular equipment will be listed, like pressure high, temperature high, and then what will happen if that pressure is high, either it may be tripping the pump or it may be stopping the closing my inlet valve. Like that, this is the cause we need to write, and then this is the effect we need to put, and then we'll put a cross mark in this. So if this is the cause, we will be having multiple, like this is for the complete unit. So complete unit will be having a number of valves, right? So for my first equipment, what is my cause? This is the first equipment, and then the related valves are here. So this is the second equipment, related valves are here. So I will close only those particular valve. So in case of main emergency, so in case of say like main emergency, I will close all my like valves. So you can see, you can see XXX in all the this one actions, effects. So in case of any emergency, like plant emergency, station emergency, I will close all my valves. So this is the typical cause and effect diagram. And process data sheet. Process data sheet, we used to we mentioned the equipment dimension, orientation. It is like a mix of equipment from the different discipline, piping, instrument, and then the mechanical team, and then the process team. So process data sheet for the equipment will be equipment dimension, orientation, whether it is horizontal or vertical, and then the composition, and then the fluid properties, and then operating and design conditions, and then the nozzle details and nozzle schedule with ratings, and then the sketch for the nozzle position and material of construction of the internal and then the external. And similarly for the process data sheet for the packages, we'll be giving the boundary conditions. This one boundary battle limit conditions, and then my required this one outlet parameters, what spec I need the outlet, so that they need to guarantee and then give that particular the design will be by the package vendor, and then we'll be giving our source data, and then I'll be asking my product data or the destination data, and then the scope of supply, what are the things this available with the engineering company, and then the associated system and utility data for the package, like what are the utilities available. So if we have steam or hot water for heating media, then those data will be giving. Accordingly, vendor will consider in their this one package. And process data sheet for instrument. So for instrument, for a fluid property will be for measuring. So we'll be having different instrument like flow, pressure, temperature, level, and then the analyzer for measuring the composition. So we'll be giving the fluid properties. Flow meter means we'll be the flow rate minimum, normal, and the maximum. So these and then the pressure minimum, maximum, temperature minimum, maximum. So these minimum, maximum will be getting through the design criteria, and then the design philosophy will be there till how much percentage we can take extra. Those things will be given through that philosophy. Then the design basis, and then the level setting, what is my minimum level, low, normal, high level, and high level. These are all the data we need to fill for the procurement of the instruments. And then the process data sheet for the valves. So pressure safety valve we discussed. We will be doing a separate calculation for the pressure safety valve, which is a dedicated task by the engineering team, because there will be a number of equipments. So each equipment will be having a safety device, with a different this one, like there also like n+1 safety valves will be there. So for safety valve, we'll be doing the calculation and giving the data to the vendor, and then vendor will size and then give the final data sheet for the this one procurement. They will be giving all our operating condition and then the design cases, like in case of fire, the power pressure will happen, or in case of any block discharge, in case of any power failure. We'll be working, doing all the calculations and then giving the required input to the vendor for sizing. We'll be doing our own calculation and then will be given to the vendor, and then they will give their data, and then we'll validate and then finalize for the procurement. And then control valve. Control valve is for, generally we talk like the control valve for the pressure. We'll be controlling the pressure through a control valve, controlling through a flow through a control valve, and controlling level through a control valve. So we'll be giving relevant parameters for the different control. Pressure means to maintain the pressure, I need to leave this much flow. And then the pressure drop for a control valve, inlet pressure, and then the outlet pressure, downstream pressure, and then the fluid properties. All those data we'll be giving it to the control valve vendor. Then they will size and then give the control valve to us. Then interface with the other disciplines, HSC. So we do our process design, so considering process in mind. So there is also multiple disciplines involved, like HSC, piping, mechanical, electrical, instrument and process control, civil and support, and telecommunication, like safety, health safety and environment. Say we talk, right, we can, whether we can drain a hydrocarbon in the open atmosphere, whether we can vent a gas, process gas into a open atmosphere, we cannot, because these things will be studied and then put some regulation and then put some safety device. If anything leak happen, all those things will be done by HSC team. And then the safety in the sense, like say if the noise is coming more, then they need to put, we need to use that we need to block our hairs through this one air plugs, and then similarly in case of any high heat area, then we need to wear some special suit to go into that area. Those things will be defined by the safety team. And then the environment. So environment in the sense, if any gas leak is happened, then if any fire happened, so what is the protection measure is there in the plant, like activation of the detectors and then the activation of the sprinkler system, fire protection system. Those will be covered by the HSC team. Then the piping team will be preparing the plot plan. We'll be doing all the thing in the paper, and then the paper in the sense doing the soft works, and then the piping team will do it in the this one 3D. Take the plot plan and then the make everything in a this one model. Everything will be finally the whatever the process design, the P&ID will be put in the, finally it will be put in the 3D model, like how we see a house in a 3D model before going for a construction. So piping team is like similar to the process. There will be a dedicated piping team for the complete project for each unit. And for them, we'll be giving our input, like that P&ID, and then like all the disciplines are like working with in coordination with each other. And then the mechanical team, like all the static and then rotary equipments will be handled by the mechanical team. Like we'll be in coordination with them. We'll be giving the data to them, and then we'll be validating the data from them. And the electrical means we'll be having pump, compressor, and then the plant will be having some this one lighting system, and HVAC system will be there. So those things will be carried out by the electrical team. And then each equipment will be having earthing protection, and then the lightning protection will be there for each plant or for particular common set of units. And then the instrumentation process control. So whatever we do put in our paper, then those things will be implemented by the instrumentation team and then the process control team. There will be a separate team for that. And then civil and structural team will working for that. Like all the equipments will be rest on the some foundation in the layout. So those calculations and then the foundation calculation, all those things will be done by the civil team, and there will be a huge number of pipe racks will be there which carrying the pipes. So pipe racks, and then the outside plant pipe racks, all those things will be taken care by the civil and structural team. And telecommunication team is the team who support for the communication from the operation team to the DCS team. There will be huge communication involved in a plant. That means for the person to person and from the plant instrument to the DCS panel. So all those things will be carried by the communication team. I think we have covered the PFD in this slide in this presentation itself. So we can go for a question answer directly if people any have.
Thank you, sir. Thank you for the great session. So we'll move on to the Q&A. If you have any more questions, I am posting the link once again. You can post your questions there. Posted the link on the chat box. So if you have questions, you can just post there. Meanwhile, we'll take the questions that has already been posted. So how P&ID is drafted, which process design application is used?
Okay, can you repeat, ma'am? How P&ID?
How P&ID is drafted and which process design application is used?
Yeah, P&ID, for P&ID, there is one software called AutoCAD is there, which is a conventional method. Nowadays, additional some smart plant softwares are there. Basic software is that AutoCAD, which you might have students might have worked in colleges. AutoCAD is the P&ID, and this P&ID will be drafted by the designers, not the engineers, chemical engineers.
Okay, sir. List all the instrument needed for process engineering related to flow measurement device.
Can you repeat, ma'am?
List all the instrument needed for process engineering related to flow measurement device.
Yeah, flow measurement, just we need only flow meter. And to say, for example, if it is a liquid is like liquid is incompressible, right? So gas is compressible. So gas, so the flow will vary based on the temperature and pressure. So if you put a flow meter in a gas line, and then if the pressure and temperatures are varying, then the flow will also vary. So we will take a compensated flow for a gas. That means flow meter along with the temperature and pressure transmitters are required for a gas measurement. For a liquid, only one flow meter is sufficient. For a gas, we need a flow meter along with the pressure and temperature measurement on that particular area.
Okay, sir. Will MSDS and its effective causes to environment will be considered during process design?
Yeah, MSDS will be the first thing. Since we are talking like the refinery, so we will not be like we have not gone like if we are going for any like downstream like a small plant and all. So they start with the design with the MSDS only, material safety data sheet. So where the design need to comply with the complete the MSDS safeguarding what they have mentioned, whether it is toxic or whether it's a class 1 chemical. So design will be considered based on the MSDS.
Okay, sir. How payback period will be considered during process design?
So payback point of view, that process we know it. This one look into that. That will be considered in the feed. Say for example, if I am going for a design of a refinery, so the refinery from the design to the construction completion, say commissioning, say if it takes 5 years. So 5 years, say some 50,000 crores are invested. So, so in the feed stage itself, they will fix everything. So my design need to finish in 1 or 1.5 years, and then my construction need to finish in 2 or 2.5 years. So after my complete construction and commissioning, so I will be taking my return in 2 years. That return means that my principal amount in 2 years. After that, whatever I take, all are my this one profit. Like that, everything will be pre-calculated during that feed stage itself. And say, for example, if this is why all the design team, design or engineering companies are working under pressure. Like they need to meet the deadline. If we delay the design, then the engineering and then the procurement will be delayed, and then the construction will be delayed. So they will follow the strict schedule. This one, that EPC companies. So say, for example, if the project is delayed by 1 year, then accordingly that means the EPC company will be given certain time limit with like fine and all. If they are delaying, then they will be their charge will be reduced, something like that. They'll be in agreement accordingly. These are the, we no need to take care of that. Process engineer no need to take care of that payback time and all. These are the things done by the management at the initial stages, because the money involved is very huge.
Okay, sir. What is the difference between normal valve and control valve, like size, MOC, etc.?
What is that?
What is the difference between normal valve and control valve?
Yeah, normal valve means valve means like we used to operate through, like in a household we used to operate through our hand, right? Similarly, in the industry, normal valve means like it is operated through a operator. A person will go and operate the valve, open the valve or close the valve. Okay, and for a control valve, say for example, if you need to reduce the temperature, then you cannot send a person go and operate the valve, because the size of the valve may be huge, like 10 inch, 20 inch. So say for example, if you want to close a 20-inch valve with one person, it takes 8 hours with a rest in between for him. So we cannot operate, we cannot use this manpower for this one to operate the valve in case of controlling the process. So you need an automated valve where it will be operated through instrument air, pressurized instrument air. So it will be operated through instrument air, generally in instrument air in industries.
Okay, sir. In the process industry, the indication of valves and controls may vary due to range value or controller system. In a process industry, the indication of valves and controls may vary due to the range value of controller's system.
The process industry. So I will just
whoever has given this question, can you please come on chat and elaborate?
Actually, controllers are like a soft one. Controllers, we will be having instrument in the field, and then signal will be taken to a soft like in a computer where that controller will be there. Controller means it is like a software. It will take the pressure signal and then it will give the signal like unit that to the valve, like you close 20%, close 10%, like that it will give the signal. So that then it will close the valve. Say consider we take a level. It will take level, my level is going 80%. So we need to, in the case of level going high, we need to open the valve. So it will give signal to the valve and then it will wait for the response. So it will give signal, say it will give signal, you open the valve to from 50 to 60. And then see, and then it will sense that whether my level has reduced or not. Then if not reduced, then it will give again signal to increase the valve further, open the valve further. So this is the controller activity. So like it is like automated one.
Yes, sir. Next question is how to find the passage route of fluid or fluid in a P&ID diagram.
Yeah, passage route means the P&ID, like say for a plant, it may be like 50 to 100 P&IDs will be there in a plant. So plant, initially we will start with the battery limits. Whatever the raw material we take, like I will take a crude oil, like we can say it as like a crude oil, and then we take utilities like cooling water, instrument air, nitrogen, and then we take steam. So, and then similarly, we have the products. We have diesel, petrol, LPG, all the products will be there. So all those things will be put in a battery limit. So all those things in a plant, it will be like put in a battery limit where all the feed and product enter in one place. It may be going through different equipment, but it will pass through the unit through the battery limit. Similarly, in the P&ID, we will be having the first starting P&IDs will be the better limit P&IDs. Starting 2-3 P&IDs based on the number of equipments and all. It will be having 2-3 P&IDs for the better limit. From that, it will start. Each time will start. If you take a crude oil will start with the better limit and it will go to heater. Like that, we need to trace the P&IDs.
Is it necessary to learn design courses to be a process design engineer?
Not required, because say if you are a fresher engineer, so if you get an offer in a company, you can go and learn, because whatever the thing I have talked, you people cannot go and do the work directly. So it is like 1 or 2 years it will take to understand the system itself. Even if people work for 2 to 3 years only for the relief valve calculation. It is like over a period of time, like after 5 or 10 years, we will be knowing who are working in the engineering. So they will be knowing complete engineering, all the calculations, all the deliverables. That means P&ID, cause and effect, and then the pump calculation, compressor calculation, and then the line sizing, PSV calculation, all, and then the blowdown. So all the calculations will be completed by a process engineering. If a person joined this year, after it may take 5 to 10 years to learn all the things through different projects. And for say for example, this course, say if someone is working in operation, or say if someone want to shift the work profile from production unit to that this office work, so they can learn these things, because already they are working in the plant, so they know all the equipments, they know all the process condition and all. Thus they should show the interest for the learning, like the calculation part, all those things, and then the deliverable point of view, like the P&ID and all, they will be seeing in the plant. So all those things they will be knowing. So only they need to show the interest for the learning point of view. Then they need to start their career in it. For that, they need to have this one. They need to attend this course.
Are the P&ID diagrams of the plant done before the construction of plant or after the construction?
No, the P&ID will be done before the construction of the plant. This will be input to the other discipline. Finally, the construction will be having like the execution thing, like execution mean for the piping, it will be isometric. For the equipment, there will be equipment GA will be there. So different drawings will be generated for each construction. And P&ID, with the P&ID, you can, a process engineer or any engineer can go and trace the thing. Okay, this is the line starting from that better limit from at this place, and this line is going to which equipment, first equipment. So with the help of P&ID, we can trace the line, all those things. We can monitor the construction, everything. But P&ID will be prepared. It's the first document for this one. First document for the construction people.
Can a production engineer with 5 years can change the profile?
Yes, ma'am. If they have the interest for this one learning, because I said like it will take 5 to 10 years to know all the thing to work. Even many people may not be work, because some of the people worked in upstream, some of the people work in refinery, some of the people work in non-oil and gas. So each people will be having different experience. So wherever they go, they learn new things there. So the learning will be keep on we should have that motive, like keep on, we need to learn. So with that, if we have that motive, then like they can shift.
Okay, sir. I think that's all. Any more questions? I hope we have answered all the questions that were posted. Any more questions? You can unmute or you can put it in the chat. Okay, so I think that's it for the questions. Thank you so much, sir, for spending so much of time and giving us great learnings. Thank you so much. It was a very great session. Thank you everyone for your actively participating. The assessment for today's module will be conducted tomorrow from 11 to 11:30. Kindly all participate in the assessment. Thank you, sir. material that I've shared in the chat will be shared in the WhatsApp group also. So those who have not been able to download, you can download it from the group. No problem. So thank you guys. Thank you for the participation. Thank you, sir.
Thank you, ma'am. Thank you.
Tomorrow also you'll be having the session. Tomorrow we'll start with piping and instrumentation diagram part 1 from 5 to 7. So please make sure you attend the session. Thank you guys. Attendance link has already been shared. For those who have not been able to mark the attendance, I'm going to share the link once again in the chat. You can mark the attendance. Those who have marked the attendance can leave. Attendance has been shared in the chat. So if you have missed, anyone have missed to mark the attendance, please mark it now. I hope everyone has marked the attendance. We'll end the session. Thank you, everyone. Thank you, sir.